Today, I look at the Born-Haber cycle, a topic which many teachers may see as one to be covered purely theoretically, where you guide students through a diagram with definitions. But today, I invite you to come into my classroom and take a different approach to studying the Born-Haber cycle. My apologies for the quality of the video as I tried to record my students while guiding the lesson. But let's move in and take a closer look. We have these three terms here on the board: hydration and solvation, lattice and solution. And then we have this diagram here, this Born-Haber cycle. So where would you put in the term solution? What happened when you put the sodium hydroxide in the water?
The starting temperature was 28.5, right? But then when we, as we put the sodium hydroxide in the water, the temperature started rising until it reached 29.8, so it's increasing gradually. So it just shows that the reaction was exothermic.
What is being formed in there, Janvi? What is being formed in the beaker?
Sodium hydroxide.
Right. And what ions do you have in there, Vaishnavi?
Sodium ions and hydroxide ions.
Okay. So what state is the sodium hydroxide in to start with, Kavya? That sodium hydroxide. Hold up the bottle. Have a look. What state is it in? Solid, liquid, or gas?
It's a solid, yeah.
Right. It's a solid, right? And then as we put it in there, it's going into...
An ion. It becomes a solution.
It becomes a solution. So then, is the process exothermic or endothermic, Noor?
Exothermic.
So then, what would we say about the enthalpy change when that goes into solution?
Delta H is negative.
Delta H is negative, symbolizing an exothermic process. Okay, so we're ready to talk about the lattice enthalpy. Right. In front of us today, do we have the starting point of this diagram? Yeah. Sodium hydroxide. Do you think it's feasible for us to make the ending point of the diagram in this lab? That's difficult to do. But if you look at what you have in your hand there, Kavya, hold it up, and you look at this part of the cycle, could you actually write a sentence to explain what is lattice energy? Could you explain in your own words what is lattice energy?
Because over here, this is still, there's a bond between water and the Na plus, or water and the OH minus, because it's aqueous. So to break that bond between...
No. You don't have to look at that. You're looking at what you were holding up.
Yes, that's...
The thing that you were holding up from the bottle.
Oh,
Does that have any water in it?
no.
It's a solid.
Yeah.
Doesn't the diagram show that it's a solid?
It's just gas.
No.
It starts with solid, yeah.
The starting point, the bottom. And then it's going straight to what?
Gas.
So what then is this lattice enthalpy change? Delta H with the subscript lat. What is it? From a solid,
To gaseous state.
from solid sodium hydroxide, it's combined like as a crystal, as those pellets that you have, into gaseous ions. And the energy change, the enthalpy change when that happens. We have selected the solution sticky note, and we've left back the hydration and solvation, and we've left back the lattice enthalpy. Solution is what we just demonstrated when we dissolved the sodium hydroxide solid into water.
That's because when the solid sodium hydroxide is added with water, the sodium and hydroxide break their bonds and form sodium ions and hydroxide ions as when they react with water. And that's because it's an aqueous, it's a solution.
Well, the question I have for you, Noor, what do you know about bond breaking? Exothermic or endothermic?
Bond breaking is an endothermic process. So,
Correct.
So it requires energy to be broken. But here, this overall would be an exothermic process because the bond forming would be greater than the bond.
Well, where is the bond being formed? That's the whole thing that some people might be confused about. I don't know if you are confused about it also.
Yes.
You're confused about it. You're not sure.
Yeah.
Because you know that bond breaking requires energy. You know that sodium hydroxide is a solid structure, which we have here, right? Flakes. So that has to be broken up. That has to come into aqueous solution. It came into the water. So even though you see all of these other things on the diagram, right, let's not pay attention to any of those as we try to explain why this process was exothermic. Because all we did was go from this to this. So something has to be happening right there in that part of the diagram. This enthalpy of solution, that explains where the bond making is. Anyone thinks they know where the bond making is happening? Think about what is the sodium ion going to be like if you were a sodium ion with your positive charge in the middle of a beaker of water. What would surround you? The Na positive can be surrounded by water. Is that some kind of bond making that's happening there? Would you agree? No, well, there's
Still a bond. There's still attraction between.
a shell of water molecules that's forming around, and that is then the only way. We have to consider it as a very exothermic process, because that is the only way that we can justify what we have seen here, right? Which is why it's important to see it here in the experiment first, and then we can go here and discuss all of these things. Because if you're just looking at this like so, you would just be memorizing that sodium hydroxide forms these ions in solution here, and that has a delta H of solution that is negative. But then when you start to reason things out and you wonder why is it so, it might not make sense to you.
Hydration and solvation.
Let me see it, hold it up so I can see it. Hydration and solvation. And then here on the diagram we have, it says hydration only, but we're going to refer to it as hydration slash solvation.
Do they mean the same thing?
Technically they mean the same thing, but there's a difference. And we've already looked at delta H solution to start with today. So could you possibly explain in your words or whatever you think it is, the difference between hydration and solution?
Well, solution is basically you're diluting, is like a solid to an aqueous solution, but then hydration it shows it's going from a gaseous ion to an aqueous ion. So it must mean the bond forming, the amount of energy it needs to form a bond between sodium ions and hydroxide ions, because it's a negative delta.
Right, but it's clearly different in terms of what the starting point, isn't it? What's the starting point when it's solution?
Solid.
And what's the starting point when it's hydration?
A gaseous ion.
Gaseous ion. Right, so that's the main thing. If you see the diagram here, the diagram shows that for enthalpy of solution, you have the solid sodium hydroxide forming aqueous ions in aqueous solution. And then for hydration, it's completely different. It's not a solid sodium hydroxide. You're looking at going from these two ions in the gas state and then putting them into a solution, an aqueous solution. Again, is that something that you think we can do easily in a chemistry lab? Na plus ions, and if you get it and you get it into solution, right? You're talking about getting sodium into a gas. Which of these three things here is the easiest? There's no which is the easiest.
The solution.
Right, it's the solution, and that is the one that we actually did.
Yeah.
Key aspect of today's lesson was the collection of data on the exothermic reaction at the very start. And this allowed us to transition into the rest of the discussion on the Born-Haber cycle. But it's important to note that the entire discussion was built around the starting point, which was based on the collection of experimental data. And this allowed for many more of the criteria on the good science teaching checklist to be met.